Hello, and thank you for joining us for this ArcGIS GeoEvent Server technical workshop. My name is RJ Sunderman, and I'm here with Gregory Christakos. In this session, we will take an in-depth look at one of GeoEvent Server's key capabilities, real-time analysis. We have a lot to cover today in a very short time, but before we begin, I would like to take a quick look at our agenda and also call your attention to a couple of terms to make sure that we're all on the same page. In this session, we'll be discussing GeoEvent Server, your on-premise solution for real-time capability within ArcGIS Enterprise. I will begin with some basic concepts to introduce what we mean when we talk about real-time analysis. We will also walk through a couple of demonstrations, taking some time to review specific processors and show you how different filters and processors were configured for each demonstration. We will conclude with some references to resources, and since this workshop is being delivered virtually, invite you to contact Greg or I with any questions you may have. To briefly mention terminology, I'll offer that real-time analysis is the process performed by a combination of one or more configurable filters and/or processors within a GeoEvent service. In this session, we'll be focusing on GeoEvent Server and the analysis you can perform on event records received in real time. A real-time analytic is an item type for ArcGIS Analytics for IoT, our new real-time software as a service offering for ArcGIS Online. A real-time analytic performs processing on data being ingested via a feed, which is another type of item being introduced for ArcGIS Online. The two terms are very similar, and I've been using analytic to refer to GeoEvent Server's capability for quite a while, but it is important that we begin to distinguish between the two when discussing ArcGIS GeoEvent Server versus ArcGIS Analytics for IoT, so that Esri staff and customers alike understand whether we are referring to an on-premise solution or the software as a service solution. Let's get started then with performing analysis in real time. GeoEvent Server is a server role for ArcGIS Server, a component within the ArcGIS Enterprise. GeoEvent Server has 5 key capabilities. Configurable inputs enable you to ingest data from sensors, both sensors in a fixed network such as those used to monitor weather or our environment, and mobile devices such as GPS and telematics sensors installed in a vehicle. A second key capability, configurable filters and processors, enable you to design and apply analysis for event records you ingest. This is the focus of this afternoon's technical workshop. Data from event records you process can be persisted as feature records in a geodatabase. Both a traditional relational geodatabase, such as Postgres, and the spatial temporal big data store are supported. You are not required to save data as feature records in a geodatabase. GeoEvent Server does not inherently hold onto or store data. You can use different types of outputs, such as a stream service, to provide different options for data visualization. Finally, you can configure GeoEvent Server outputs, which are capable of making REST requests on an external endpoint, enabling you to send data to devices and drive action within an environment. Here we see an illustration of a GeoEvent service. You configure and publish GeoEvent services using the GeoEvent Manager, a web application we will look at briefly during our first demonstration. A GeoEvent service must have at least one input. Inputs are configurable. You choose an appropriate input connector based on the format of the data you want to receive and how the data will be received, for example, as part of a REST HTTP post request or sent to a TCP socket. Every GeoEvent service must also have at least one output. As you can see illustrated here, you can configure multiple outputs to broadcast event data as feature records using a stream service, at the same time as you perhaps add or update feature records in a geodatabase, or generate email alerts as conditions are detected. You simply configure a different type of output and then include that output in your GeoEvent service. The real-time analysis you perform depends on processors and filters you incorporate into a GeoEvent service. Highlighted here is an incident detector, one type of processor you might configure depending on what you need a GeoEvent service to do. Filters can also be included in a real-time workflow. The job of a filter is to evaluate a condition and discard any event records which do not satisfy the filter's condition. Let's take a look at an example. Here we see some hikers moving around different areas of interest. The hikers are all carrying some sort of device which is broadcasting their location. These location reports are the event data GeoEvent Server is processing. As a hiker leaves one area and enters another, you will see a yellow alert displayed on the web map. If a hiker's location is detected outside all of the established geofenced areas, a different type of alert is generated. This is real-time analysis, ingesting event data from sensors, applying configurable filters and processors to the event records to detect conditions of interest, and then pushing the processed data to feature records for display. In this example, the event records were broadcast to a stream layer for visualization using a web map. GeoEvent Server includes almost 24 configurable processors out of the box. There are processors which create buffers or extents around an event record's geometry, processors which calculate values, processors which modify an event record schema, and processors which monitor conditions. Each of the out-of-the-box processors have configurable properties. You can arrange them in series or in parallel in a GeoEvent service. Adding and configuring filters and processors in a GeoEvent service, in a way, is like developing a geoprocessing tool using ArcGIS Desktop or ArcGIS Pro. You design your analysis as a workflow by dragging and dropping different filters and processors into a new service, and then publish the GeoEvent service. There are also samples of different processors available on our GeoEvent server gallery. These samples were all developed using the GeoEvent server's Java SDK. Several of these processors have their source code implementations available in GitHub. These are available for download if a Java developer on your team wants to extend a sample with custom behavior or use it as a pattern for developing a completely new processor for some unique task. Filters allow an event record to pass only if the event record's attributes or geometry satisfy a condition. Filtering conditions are constructed using an expression builder and saved as part of the filter's properties. Filters can refer to attribute values, checking, for example, if an attribute's value is greater than some constant. Attribute values can also be checked to see if they are null or if they match a regular expression pattern. You can use a filter to check if an event record's geometry shares a spatial relationship with an established area of interest. Event records whose geometry intersects a specified geofence, for example, may be allowed to pass through a configured filter. You can also use Boolean logic to construct more complex expressions. Illustrated here is an example of a filter which checks to see if an event record's geometry is both disjoint all geofences in a specified category and that the event record's count attribute is not equal to 0. Filters are different from processors in that the job of a filter is to discard an event record which fails to satisfy some condition. Processors, on the other hand, usually modify an event record in some way. Some work primarily with attribute values, while others work only with an event record's geometry. For example, if you wanted to convert a value in degrees Fahrenheit to Celsius, you would use a field calculator. If you needed to enrich an event record with values from a secondary table, you would use a field enricher. Some processors only work with an event record's geometry. A buffer creator, for example, would be used to construct an elliptical buffer about a polyline or polygon received as an event record's geometry. Other processors act as monitors and look for specific conditions. A track gap detector, for example, remembers event records it has seen with a specific track ID and generates new event records when expected event records are not received within a specified period of time. I have mentioned the use of geofences a couple of times, so it would probably be good to take a quick look at the sort of expression you might configure a filter or one of the monitoring processors to use. Every spatial expression you configure must refer to one or more geometries which have been established as a geofence. A pair of regular expressions specify which geofences will be considered. In the expressions illustrated here, the first dot star in the pair matches one or more geofence category names. The second dot star matches one or more named geofences in the selected categories. The selection of geofences to consider must not be confused with the qualifiers applied to a spatial relationship. In the first expression illustrated here, if an event record's geometry intersects any of the candidate geofences, the expression will be satisfied and evaluate true. In the second expression, an event record's geometry must be disjoint all of the candidate geofences, otherwise the expression will not be satisfied and will evaluate false. Looking at a specific example, say we wanted a filter to allow only event records to pass if the event record's geometry intersects any geofence in a category named hazard zone. Such a filter might be used if we wanted to alert when a trackable asset entered into a hazardous area. Another solution might want a monitoring processor, like an incident detector, to open an incident and begin tracking the duration during which a trackable asset is outside or disjoint all established safety zones. The examples on the previous slide bring up an important point about geofences. Sometimes geofences overlap, and sometimes they are separated by some distance or share a common boundary. This can influence which qualifier you apply to a spatial relationship. For example, imagine you have a vehicle or other asset that periodically reports its position. You could configure an expression that evaluates true when a track point intersects any geofence, as long as the geofences do not overlap. But if you wanted to determine if a track point intersects all geofences, the geofences would have to overlap so that the single point could intersect all of the established geofences at the same time. Illustrated here are a dozen different spatial operators you can use to configure a spatial expression. You can configure a filter or a processor to do something when an event record's geometry is inside or outside a specified geofence. The operations intersect and disjoint are equivalent to inside and outside respectively. Geofences do not have to be polygons modeling an area of interest. If a geofence is a polyline, such as a coastal boundary for example, and an event record's geometry is a polygon, such as a storm's anticipated area of effect, you could test to see if the event's geometry crosses the geofence polyline. A word of warning about a couple of the spatial relationships listed on this slide. If you consider that a geometry is generally modeled as a collection of coordinate values, which are floating point values, and you really should never compare one floating point value to another to see if they are equal, then you should be very careful about using a Clementine relationship such as touches or equals with location data from sensors which can be imprecise. It would be better to buffer a point to establish a tolerance and ask if the buffered point intersects a geofence, then ask if a received point location touches a geofence. Two of the spatial operators GeoEvent Server supports are set apart because they consider state. Generally speaking, GeoEvent Server does not cache or hold on to any information about the event records it processes, but in a few exceptional cases it must, and the enter and exit operations are two such cases. A filter or processor must know if an event's geometry was previously outside to determine if an enter condition should evaluate true, for example. The inclusion of stateful processors and filters can impact not only your GeoEvent service design, but your overall system architecture and design. Geofences are imported from feature records. You can store feature records in a feature class, and use GeoEvent Manager to perform a one-time import by pulling the feature record set through a feature service. This option is good when geofence geometries are relatively static, like administrative areas, state boundaries, facility footprints, or the location of fixed critical assets like radio transmission towers. You can also configure a GeoFence synchronization rule to periodically poll a feature service to refresh the geofences registered with your GeoEvent server. This is the same as a one-time import, except that GeoEvent Server automates feature record set retrieval for you by polling the feature service at an interval you specify. This option is good when geofence geometries occasionally change and you need event records being received to be processed against an updated set of geofences. There is a challenge here that you need to recognize, however. You cannot configure the GeoFence synchronization to occur too frequently, or the synchronization activity will directly contend with the event data being ingested for processing. If you set the synchronization too far out, you risk GeoEvent services not using up-to-date geofences in the spatial evaluations and analysis they're performing. The default for GeoFence synchronization from a feature service is once every 15 minutes. If feature record attributes which drive properties, such as whether or not a geofence is active, or the start and end time window during which a geofence should be considered, or the geometry of the geofence itself periodically changes, and the spatial analysis you need to perform demands that geofences be updated more frequently, you need to consider a different approach. You can configure a GeoFence synchronization rule that subscribes to a stream service, allowing a GeoEvent server output to push processed event records to its own GeoFence synchronization. Stream services broadcast data in the same Esri feature JSON format as feature services return data in response to a client's query for feature records. If you need rapid update of geofences you want registered with GeoEvent Server, either because the geofences themselves are rapidly changing, or relatively infrequent geofence updates every quarter hour is unacceptable, consider using a stream service to push geofence updates to a synchronization. Stream service synchronization is not without its own challenges. You need to be sure, especially if uniquely named geofences are being broadcast by the stream, that geofences have an expiration date and will be actively purged. Otherwise, memory will be quickly consumed as streaming geofences fill up available RAM. Here's an illustration for a potential case where you might need dynamic geofence synchronization. Say you receive a center point location for an area of interest. You can use a create buffer processor to create a buffer around the center point. Aircraft location reports received in real time, however, are only able to evaluate against the last known center point and buffered area of interest. Analysis provided by your GeoEvent service indicates that none of the aircraft's positions intersect the geofence. Using a stream service, the moment a new location is received for the center point, a new area of interest can be established so that aircraft positions being received in real time have an updated geofence against which their position can be evaluated. Let's take a look at a demonstration using GeoEvent Server to update real-time attributes for a set of sensors at fixed positions within a sensor network. I've prepared a web map with a feature layer whose feature record set has a dozen or so point features representing weather stations. I can click on a weather station's feature to display a pop-up and see that there is no data for any of the metrics being collected by the station's sensors. I'm going to use GeoEvent Server to receive and process event data from a simulated real-time data stream to update these feature records, so I will need to set my feature layer to automatically refresh so data written to the features will be displayed on the web map. I've configured my GeoEvent server for this demo with an input, receiving text from the GeoEvent simulator, and a couple of outputs, which will use data from event records processed by one of two GeoEvent services to update feature records being displayed by the web map. I can use the simulator to send several event records to GeoEvent Server. As data from the sensors is processed through the GeoEvent services, we see their event record counts increment. Notice that only the second service is routing events it has processed to an output. Station metrics are being updated, but not alerts. Looking at the GeoEvent simulator, the last record sent was for Miami. So if I click to examine that station's feature record in the web map, I should see the last observed metrics for that station's sensors. Sure enough, Station Miami has been updated, while other stations such as Phoenix or Sacramento do not display any data because real-time data has not yet been received for those stations. The second part of my demonstration involves alerting and notification. Here in GeoEvent Manager, you'll notice that my alerting GeoEvent service has received several records, but no event records have been processed through the service or routed to its output. If I use the simulator to send another dozen or so records, you'll notice that now we have an alert record output. Let's take a look at the web map. The Denver station is displaying an alert that wind gusts have exceeded a predetermined threshold. The Miami station is not displaying an alert because no value has been set for its display code based on analysis performed by the alerting GeoEvent service. As data continues to stream into GeoEvent Server, we will see other stations pop alerts for wind gusts and/or display all clear flags as wind gusts calm and wind advisories can be allowed to expire. Illustrated here is the GeoEvent service responsible for receiving sensor data. Let's take a look at the service's key processors, the field calculator and field mapper. A field calculator is one of the configurable processors available out of the box. You'll want to use a field calculator when you need to calculate new values or perform string manipulation on data received and adapted by an input. Results from the processor's calculation can be written to a new field or used to update data in an existing event records attribute field. The field calculator is one of the simplest yet most versatile of the available processors. It supports several functions as part of its expression, some of which accept regular expression patterns, which can be used to perform powerful string manipulation and formatting. Here we see an illustration of how I configured the field calculator for this demonstration. The date timestamp in the simulated sensor feed is reported as an integer in epoch seconds. So I use a field calculator to scale the timestamp by 1000 so that its value represents epoch milliseconds, which GeoEvent Server uses for date values. The calculated result is written back into the epoch attribute field to update its value. A field mapper is another of the basic processors you will use early as you begin designing and publishing GeoEvent services. You'll want to use a field mapper when you want to change the schema or structure of an event record. The processor specifies how values from one schema or structure are mapped or copied into a different schema or structure. Here we see an illustration of how the field mapper was configured for this demonstration. Notice the difference between the attribute field names on the left, the source, or event record received by the processor, and the field names on the right, which are the target. Very often, we receive data and have little or no influence over its structure, hierarchy, or attribute field names. When needing to use the event data to update feature records in a Postgres database, as I am doing here, I need to map the data received to attribute fields whose names are all in lowercase. The second part of my demonstration had to do with alerting. As you can see here, there are quite a few more processors and filters involved in the analysis. Let's take a closer look at how the key processors, field mapper, field enricher, and a monitoring processor, incident detector, were configured for the demonstration. I am often asked whether it is best to place a field mapper at the beginning or at the end of an event processing workflow. The answer is, it depends. You can use a field mapper immediately following an input to add fields to an event record schema. I call this strategy pre-mapping. It guarantees that fields I will need later exist in the event record schema so that I can write to existing fields rather than expecting processors downstream to create new fields for me on the fly. On the other hand, you will often use a field mapper as the very last processor in an event processing workflow because you need to adjust the schema of an event record to match the schema expected by a feature service. If you route event records to an output that requests a feature service add or update feature records, and the feature service does not recognize the fields in the request, the feature service will simply reject the GeoEvent server's requests. Finally, you might sometimes want to simplify an event record schema. Maybe certain attributes in event records being received are not included in a feature service's schema. You could use a different processor, a field reducer, to remove the unwanted fields, but I prefer using a field mapper to map fields from one well-known schema or structure to another. Here we see an example of my use of a field mapper to pre-map an event record schema to prepare it to receive enrichment values. Again, I want to write to existing fields whenever possible. Note that the geometry field has been left unmapped. When you leave a field unmapped in a field mapper's configuration, it is the same as explicitly writing null into that field. If I were to send this event record to the output used to update feature records immediately, I would replace a valid geometry in the feature record being updated with null, and that weather station would disappear from the web map when the map next refreshed its content. I'm not going to leave the geometry null, however. I'm going to use a field enricher to fetch a value for the field. A field enricher processor is used when you want to perform an attribute join to retrieve data related to an event you are processing and copy the data into the event record, enriching it with new values. There are two variants of the field enricher. The first, and the one I'm using here, retrieves its enrichment values from a feature record maintained in a feature class. The data being simulated has no geometry. It is non-spatial. This is a reasonable expectation when sensors are fixed in place and not moving. I can retrieve the geometry from the weather station features and use it to enrich the non-spatial data I am receiving and processing. Here we see the configuration for the Field Enricher feature service processor I included in my analysis. The processor is using its default registered server connection to identify a feature service in the root folder named Weather Underground Feature Record. It queries the specified layer looking for a feature record whose station ID, all in lowercase, consistent with the geodatabase's schema, matches the station ID, mixed case, of an event record being processed. If a suitable feature record can be found, its geometry will be retrieved and written into an existing field in the event record. The Field Enricher feature service employs a cache to remember data queried from individual feature records. By default, the cache will hold up to 1,000 such feature records, and will query again to retrieve any updates when any individual feature in the cache is more than 60 seconds old. This strategy ensures that the processor makes efficient use of memory, only querying for and caching data it needs for event records it has received and needs to process. On the one hand, this is very good, as the processor will not pull a large number of feature records from a database into memory just in case it needs them. On the other hand, this can be viewed as inefficient, as the processor is querying for records as it needs them one at a time, rather than batch loading the entire feature record set. This is behavior you should be aware of when using this processor. An incident detector is one of the monitoring processors. It is more complicated than a field calculator or field mapper, but it provides a powerful capability. It can recognize when data satisfies a specified condition and track how long that condition is satisfied by looking at additional event records as they are received. You'll want to use an incident detector, when you care both that a condition has been observed and want to monitor how long that condition remains in effect. A rule of thumb would be to use a filter when you simply want to test if a condition is true or false, and discard event records which do not satisfy a condition. Use an incident detector when you care more about tracking the date-time a condition was last observed, and the duration of the condition, than attribute values other than the asset's track identifier and geometry. The schema of an incident event record is very different from the schema of whatever sensor data you are receiving and processing. Because this processor maintains state and updates incidents it creates based on event data it observes, you should be familiar with the life cycle of an incident. An incident is created when an event record is received which satisfies an incident detector's opening condition. An incident is only updated as subsequent event records are received by the processor, allowing it to check if the opening condition is still satisfied. An incident will be closed when an event is received which satisfies the processor's closing condition. Incidents may also be administratively closed when no further events are received for a given asset's track identifier within a specified period of time. You can think of this as allowing an incident to expire when no further updates are actively being received. The use of an incident detector can be somewhat intimidating, so let's show its operation as an animation. Suppose we have an area of interest, some area that we care to be alerted both when a tracked asset enters and how long the asset remains in the area. As an event record is received, it does not intersect the area, so there is no event output from the incident detector. Another event does not intersect, there is no output. But when an event does intersect the area, a new incident record is generated. Notice the schema is different. It has a status of started. As assets dwell within the area, the incident record is updated to a status of ongoing. Notice the duration is also incremented. A fifth record is received. Our tracked asset is still in the area, so our incident is still ongoing. The duration continues to increment as new events are received, and the incident is ended once the tracked asset leaves the area. Additional event records can be received, and no output comes from the incident detector because its opening condition is not satisfied, so there is no need to create a new incident. In my original concept for the alerting demonstration, I wanted to acknowledge that windy or hot could be perceived differently in different parts of the country. That was the reason I wanted to enrich each event record with the geometry of each weather station, so that I could use a spatial filter to show that analysis could be tailored for different regions or different areas of interest. This made the event processing workflow unnecessarily complicated for what I would like to show here, so I'll ask that you imagine how the filter illustrated might be changed to see if metrics from a particular station could be handled differently based on whether an event record's geometry has a more northern latitude or a more western longitude. To simplify the demo, the filter is actually ignoring the enriched geometry and only checking if a specified attribute field exists. If the filter's condition is satisfied, event records are routed to the incident detector. Any event records failing to satisfy the filter would simply be discarded. The incident detector associates an asset's track identifier with incidents it creates. This means that in order to use an incident detector, your event data must have a track ID. If an incident exists for this event record's track ID and the processor's opening condition is satisfied, the existing incident will be updated. The incident detector, as it was configured for this demonstration, is illustrated here. Any event record with a wind gust greater than 30 miles per hour will trigger a new incident to be created or an existing incident to be updated. If the value of the event record's wind gust is less than 30 miles per hour, an existing incident will be closed or the event record will simply be ignored. By default, All incident detector processors use the cumulative incident type. This simply means the duration and status should be maintained as I've been describing here. The other option for this property is point in time, used when you want an incident to be created when a condition is observed and then immediately closed with 0 duration. This makes an incident detector behave a little more like a filter. The geometry type does not refer to the received event record's geometry type. The choices for this property are point, multi-point, or polyline. This processor has a bias for receiving point locations and modeling an incident's history with point, line, or multi-point output. In this demonstration, I use the default point type, but as you'll see in a moment, the geometry output from the processor really doesn't matter because I'm not using it for this demonstration. I configured the incident detector with an expiry time of 0 seconds. This can be a little dangerous as incidents created by the processor will never expire. But when demoing the concept, if I needed to suspend data simulation for a brief period of time to explain something, I didn't want incidents which had been created to expire just because I had not simulated any data for a few moments. The next step in the analysis is to check the status of any incident generated or updated by the processor. I do this with a pair of filters. When branching an event flow this way, it is important that the filter's expressions are mutually exclusive. Parallel filtering can significantly impact a GeoEvent service's throughput as the entire event payload is sent to each filter, allowing the filter to keep event records it cares about and discard the rest. In this case, I want to handle incident reports which are started or ongoing differently from those which have ended. A pair of field calculator processors follow the filters to calculate a value I can use as a feature record's display code. Remember when we saw the Denver display a yellow flag initially? That wasn't GeoEvent Server displaying the flag. That was the web map symbolizing feature records it retrieved from the geodatabase according to coded values which had been written into the feature record's display code. Notice that I'm using a little sleight of hand here. Each field calculator calculates a string equivalent of either 1 or 0, and writes the string into an available attribute field named Note, which the incident detector is not otherwise using. This enables me to configure a field mapper, which will copy a station report's track identifier, the computed note, and an incident duration into attribute fields consistent with a feature record schema. What I'm doing with this field mapper is both subtle and powerful. If you look at the schema of an incident record, you will notice that it has over a dozen fields, most of which are not included in my feature record schema. My field mapper is therefore accomplishing two of the purposes I outlined earlier. It is reducing the incident record schema, discarding event records I do not care to output, and also guaranteeing that event records routed to the output contain only attribute fields consistent with a target feature service. Attributes which are not included in an event record routed to an add update feature output will not be modified in the corresponding feature. Using what I'll refer to as a partial GeoEvent definition, I can choose to update only the display code and duration of each feature record when the analysis I have applied to event records determines that conditions are right for an alert. I have a blog available on GeoNet which describes this in more detail. With that, I would like to hand control over to Gregory, who will share another demonstration with us examining some additional processors as he uses GeoEvent Server to conduct analysis on simulated UAV position reports.
Thank you, RJ. We'll go ahead and shift focus here now and take a look at a second use case where we'll be using ArcGIS GeoEvent Server for situational awareness and response. Specifically, you'll see 3 different demos where we'll be monitoring the use of drones or UAVs as well as their operators. And based on conditions that are important to us, we'll see different types of alerting occur based on the situation at hand. And as a result of that situational alerting, we'll see a real-time response as well. So before we go ahead and get started with the first demo here, I'd like to take a minute to explain what you see in front of you. So imagine for a second that you're a part of an engineering firm and you've been tasked with going out to the field to use drones to perform some sort of imagery collection or analysis. As a part of being a responsible drone operator, there's certain rules or regulations that you would need to abide by. For example, it would be irresponsible or maybe against the law to fly a drone within the certain amount of distance of an airport's airspace. And so in red, we see this buffered area here, which indicates just that. Essentially, we have a geofence, which is a 1 mile no-fly zone airspace area. We don't want our drones going there. In blue, you see what are building footprints. Something that tends to be a pretty contentious topic in the news these days is the idea of drones flying around residential properties. People don't want them flying in their backyard. And so while it might not be against the law to operate drones above these types of structures, maybe as a standard operating procedure for our own engineering firm, we don't want drones flying in these places as well. So the areas in blue are a second type of geofence here that's also indicative of a no-fly zone. This is a 400-foot buffered area around our buildings. There's other conditions that we might want to keep an eye on as well, such as making sure our drone doesn't exceed a certain altitude. But we'll go ahead and get started here. So here we have our real-time position of our drones coming in and being displayed. We have a breadcrumb trail that shows the last several recorded positions. And on the right here, we have our first type of alerting. Our drone has clearly entered that airport's no-fly zone airspace, and so we can go ahead and symbolize that and collect that information in real time. Here we see that there was an infraction area, event that occurred, and so we could potentially use this information to let the operator on the ground know that they shouldn't be flying drones in this area. On the left here, we see a different type of a notification has just occurred. These red bullseyes indicate an altitude warning. As I mentioned a second ago, in order to safely operate a drone, we might not want it to go over a certain altitude per regulation. And so here we see it's exceeded 400 feet in altitude, and so we've gone ahead and captured that event. Now, as this drone starts to return to its original position, it might not be actively capturing imagery anymore, but we see that it's flown over those residential areas. And so we might not respond to this information in real time, but we could potentially collect this to let the operator know after the fact that they shouldn't have flown the drone in that path. So with the first demo having concluded, you might be wondering, how is this made possible? Well, here we see the GeoEvent service that was used to make this all happen. On our input in green, we have the drone's position and attribute data coming in real time. So this would be like its geometry, altitude, speed, being fed in as some sort of delimited text. Our output, or those boxes in blue, are various stream services used to visualize not only the position of the drone, but as well as other spatial and attribute conditions, such as the altitude has been exceeded or it's entered a no-fly zone. That being said, there are additional processors that were used here, but I'd like to focus on one key processor that made this particular demo possible, and that is the GeoTagger. So at a broad view here, you'd want to use a GeoTagger when you need to enrich an event record or some sort of real-time data coming into GeoEvent with the name of a geofence with which the event record's geometry shares a spatial relationship. So to put it more simply, in the case of our demo, if we wanted to know when our drone was entering or has entered or is inside of a particular geofence, and we want to know the name of the geofence that it entered or was inside of, we would use a GeoTagger to collect that information. So this particular processor uses a spatial expression to identify those related geometries of that geofence. And it uses a unique identifier or name of the geofence, and it appends that to the event record. So essentially, we're performing a spatial join with the geofence based on the conditions we've set up. So to kind of conceptualize this a little bit more here, below we have our geofence, the Sumter Airport in red, and we just received the real-time position of our drone. Its geometry is recorded to be inside of that airport's airspace. And so what the GeoTagger will do, as we see on the right, is append a new field that I've called isInside and add the name of that geofence to the record. So now we have the information about where it was inside of as a part of that drone's data. In terms of the demo itself, this is how the processor was configured. I've given it the name tag no-fly zone. I've specified the geofence as any geofence that's of the category no-fly zone. So this means either the buildings or the airspace. And I say basically any named geofence within that category group. The spatial operator in this case is inside any. I want to know when is the drone inside any of my no-fly zone geofences. And essentially, with all the rest of the properties, I say append that name of the geofence to a new field called infraction area. And ultimately, this is how we get the infraction area field that you see in the pop-up on your left. As soon as the drone enters that geofence, the GeoTagger kicks off and it appends the name of the Sumter Airport SMS value to that infraction area field. So with that, we'll go ahead and build up on the last demo here with another drone example, except in this case, not only are we going to be observing the position of the drone, but we'll also have the real-time position of where the operator is, or specifically the device that the operator is using to control the drone. In this case, both these objects are going to be giving their real-time position to us, and we're going to capture that in GeoEvent to perform some analytics. So if we go ahead and get started here, you see again we have the drone and it's flying out to a certain crop field to do its work, but we also have the operator selected here in red. In this case, the operator is Jane Doe. Now you might notice that around us is this red sort of buffered area, this dashed line. And what this indicates is a 1.5 mile line of sight that's being dynamically generated around the operator's position in real time. And the idea behind this is as a engineering firm, maybe we take it upon ourselves to say we don't want our drones flying outside that line of sight. And so as we see here, as soon as the drone flew outside that line of sight, we can capture a different type of alerting that pertains to that event. And so while the demo is going to go ahead and cut short here, we can see some interesting information has been captured based on that drone flying outside that line of sight. So not only do we have the specific identification of the drone, but we also get a unique message indicating that there was an outside line of sight event, the time that it happened, and we were able to dynamically append the name, email, phone number, and task of who the responsible operator is based on that line of sight condition that had occurred. And this is important because if we want to respond to these conditions in real time on the ground, we want to know who is the operator that we either personally need to be contacting to let them know that this had happened, or how can we obtain this information so that way we can have GeoEvent dynamically send maybe a text or email to this person based on this line of sight condition that had happened. So what made that particular demo possible is the GeoEvent service that you see here. So again, on our input, it's the same type of concept. We have the drone's position as well as the controller data for that drone coming in. And we go ahead and filter that just so that we only get the drone's position. On our output, we have different stream services, again, to visualize the drone's position, as well as the line of sight warning that we saw. We could easily set up other types of output connectors to send out types of messages or alerts to devices. The key processor here I'd like to focus on in this GeoEvent service, though, is the Field Enricher feature service. And a little bit later, I'd like to talk more about the spatial filter that was configured for detecting when the drone was outside of that line of sight of the operator. So in the case of the Field Enricher here, how it works in the case of the demo that you just saw is that as soon as we get the data in about the UAV, in this case UAV ID 003C, that's its unique identifier, that data gets passed to the Field Enricher and it queries a feature service or a related table, I should say, in that feature service for a similar record to join on. So in this case, the UAV's ID is 003C. In the feature service, we might have a table of who all the operators are for that given day and who their assigned UAV is. And so based on these common values of the 003C, we can actually take the records from that feature service and append it to the event record as we see here. So we're able to essentially perform a real-time join on data and bring in additional information. And again, this is useful in the case of our demo, so that way when we know that the drone is flown outside a particular line of sight, we instantly have the name of the operator, their email, and their phone number to contact or have GeoEvent contact. So here's a look at the Field Enricher as it was configured for this demo. So I've given it the name get operator info. I've specified my ArcGIS server connection where that feature service lives, the folder in which that feature service exists, the name of the service, and the layer that has the data we want to essentially join and bring into our event record. I go ahead and specify the field in that feature layer to join on. And I specify that I want to bring in as new fields the name field, the email, the phone number, the task from that feature service. And I go ahead and write that out using a new GeoEvent definition to enhance my drone data as it comes in real time. I'd like to take a minute here to discuss the cache refresh time interval property and why it is important. In this case, I've configured this property with a value of 480 minutes, or effectively 8 hours. And the reason I did this is because I know that the underlying data in my feature service is not subject to change over this period of time. Who my drone operators are, the drone that they're assigned to, as well as other key values such as their email or phone number is not subject to change over the course of a working shift, if at all. Therefore, by choosing to configure my processor in this manner, I can guarantee that GeoEvent Server will issue limited queries on the feature service for each unique drone record received. In other words, the first time that my GeoEvent service receives a record pertaining to a specific drone, as determined by its track ID value, it'll issue a query on the feature service for that drone alone and store the associated data in its cache for 8 hours. If a second later my GeoEvent service receives another record for that same drone, it'll perform the event enrichment using the values stored in its cache. Again, the data will be maintained in the cache for 8 hours before another query is ever issued. Had I set this property to 1 minute, for example, I would be introducing a significant performance impact on my GeoEvent service due to the constant unnecessary queries happening every minute. You can imagine that if there were thousands of records coming into GeoEvent each second, the thousands of queries each second could easily overwhelm the feature service and severely degrade the performance of the GeoEvent service as a result. But all of this together is what allows us to get this enhanced record that you see on the right. Not only do we have the UAV's ID, its message, and the reported time that that message or that event had occurred, but we also get those extra fields, name, email, phone, and task, coming from a feature service. Now, a second ago, I mentioned that there is this drone outside line of sight spatial filter. Effectively, what we're looking for when configuring this is to see when is the drone's position outside that 1.5 mile buffer for where the operator is. And so there's a second GeoEvent service that was configured here that made this all possible. And that's what we see in front of us. So we have the drone data and the controller data coming in on a feed. And essentially, in the case of this second GeoEvent service, we're filtering for just the controller's position or the controller's data. And we can actually display that position in real time using a stream service. That's how we were able to display that red dot indicating where the operator was. But we also take that data and we send it to a buffer creator processor to create a 1.5 mile buffer or ring around where the operator or the controller is assumed to be. And with that data being updated every time we get controller position in, we can send that out to its own stream service and use that as a source of dynamic geofencing for our original GeoEvent service we just saw before. So the idea is here that you can have GeoEvent services that produce different data products that can be used dynamically in real time with one another. These things don't just exist in isolation. We won't go too much into the buffer creator here, but essentially this is how I configured this processor. I've gave it the name visible range 1.5 miles. I specified the geometry field that I want to buffer around, and in this case I said I want to buffer it by 1.5 miles as my unit. And that's again how we got this kind of red dotted line that you see here. So for our last demo here, we're going to continue with the same concept of drone usage and monitoring operators and conditions on the ground. Go ahead and get this started here. In this case, we have the drone, and it's maybe flying out to perform some sort of imagery analysis to check up on an area of forest that looks like it was recently clear-cut. So not only do we have the drone flying around in its fixed path, but we also have the operator being displayed as well. In this case, it's John Doe, and they have their assigned UAV, the device ID, etc. Now, one thing to keep in mind here is that because this drone is flying above the tree line, the operator on the ground might not actually be able to see where that drone is at any given time. You can imagine it might be pretty difficult the further that the drone flies away. And so it's important in situations like these that we have some insight into where our drone currently is, as well as what was its last recorded position in case the drone, let's say, crashes or falls out of the sky, whatever might happen. So in this case, we see that the drone finished its work and it's starting to return back to the operator, but suddenly it stops right here. And so here we have a missing drone event occur, and that information is sent back to the operator in real time with the location so they can respond to it. So we see that our operator is moving at the speed of light back to where the drone's position was last observed. And the idea here is that as soon as the operator gets to where that drone was, we can think or assume that they've collected that drone. So now as the operator is returning back to their starting position, we'll see whether or not that drone is still operable and whether or not it can continue to fly. So at this point, we see that the drone's been relaunched. And if we click on our missing drone event there, we can see that its condition has been set to false, meaning that the drone is no longer missing. There's no longer a gap in our coverage. So for our last demo, here is the GeoEvent service that made this possible. So by this point, you're probably pretty familiar with the inputs and the outputs, but essentially on our input, we have that drone position and attribute data coming in. So altitude, speed, things of that sort. On our output, we have different stream services we've used to visualize, the drone's last reported position as well as its current position. And the key processor that made this particular demo possible is the Gap Detector for detecting when the drone went missing. So in general, you want to use a Gap Detector when you need to detect the absence of an event records reporting, and also to alert or notify someone that expected data was not received. So the idea here is if you're expecting data to come in every 5 seconds, in this case, if we're expecting drone 004D to report its position every 5 seconds, and we don't get that data after a certain 5-second window of time, we can trigger a Gap event to notify or alert somebody that there's a gap in coverage or that data is no longer coming in real time. So to kind of conceptualize this a little bit further, here we have our drone's position. It comes into the system. Its track ID is 004D. A second later, the same thing, track 004D, the drone comes in. But a second later, we see that we don't actually get anything. And so at this point, the Gap Detector is going to issue a Gap event, or the gap is set to true. And this is going to continue every second that we don't actually get anything. So a second later, there's nothing coming through, so it's going to issue a new gap event. A second later, same thing. Same thing, a second later. Once we actually get an observation about our event record again, in this case, the drone 004D, the Gap Detector is going to set its gap condition to false and stop reporting gap events. And so together, this is effectively what we saw in the demo, where as soon as there was a gap in events being reported, the Gap Detector issued an event. And then as soon as that drone was recollected again, that process ceased. So if you're curious about how the Gap Detector was configured for the purposes of this demo, I've gone ahead and given it the name Detect Missing Drone, and my gap notification mode I set to on change. Now this is a little bit important than the previous conceptualized slide that you saw before. On change means that as soon as a gap event is detected, it'll issue a notice or an event outbound from the processor. And then as soon as that event actually ends, meaning we've received the data that we're expecting again, it'll send one more event saying it's, false. That's what we saw in the demo. As soon as the drone crashed, there was an event issued, and as soon as the drone was launched again and its feed was live again, it went ahead and issued one more event indicating it was false. But we could set this to something like continuous, where if every second we're expecting an event and we're not getting anything, GeoEvent, or the processor specifically, will issue a track gap event every second. In this case, the gap duration was set to 5 seconds and the gap detection interval was set to 1 second. So gap duration is basically the idea of how long do we wait before a gap is true. In this case, we're saying if a drone doesn't come in within a 5-second window, its gap duration, or it's considered to have a gap in its coverage after that 5 seconds. And then the gap detection interval is how often does the processor check to see whether or not there is an event that meets that gap duration criteria. But ultimately, using a stream service, this is how we're able to visualize these gap events. Is, when there's a missing event where it's set to true, we can display that with its own unique symbology with the stream service, and vice versa for when it's false. So I've presented all these different demos as separate GeoEvent services, but we could hypothetically combine these all into one GeoEvent service as we've seen here. And even though that there was different stream services used to visualize these various types of conditions on the ground, you could very well use something like an email or text output or some other type of output to send that string of text or delimited information to some other device, maybe the operator themselves or their device, to correct course with that drone. But ultimately, using stream services, this is how we were able to visualize the different types of alerts that you saw in all three demos, whether it was the drone's position, the red alert showing that the drone entered a no-fly zone, maybe an altitude was exceeded, exception, and things of that nature. So with that, we'll go ahead and close things out with some summary and resources. So in summary, ArcGIS is a dynamic platform that enables continuous analytics and real-time visualization for better understanding of our world. And GeoEvent Server allows you to effectively know what is happening as it happens, react and make smarter decisions faster, and be notified when interesting events occur. If you're interested in some resources on GeoEvent, we do have our enterprise pages here. We have some recently updated documentation. For example, our input and output connectors have recently been updated. And as of several weeks ago, our processor help has been revamped as well with a lot more information. So we definitely invite you to check that out. There you will also find our quick start guide, as well as some installation guides for getting started with GeoEvent. And you'll also find some system requirements and in-depth tutorials that take you through a step-by-step process of how to configure a lot of the processors and components that you saw today. Additionally, we invite you to check out our blogs and discussion forum as well at the link here. We're also very active as a team on our GeoNet page for GeoEvent, so definitely check that out as well. And for all video recordings of technical workshops, I invite you to check out this link. We understand that this is a virtual event this year, so if you have any questions, feel free to reach out to RJ or myself. We're more than happy to address anything that you're curious about as it relates to this presentation or GeoEvent in general, so please feel free to reach out. But with that, thank you for your time. I hope you learned something new about the analytic capabilities of GeoEvent. Have a great rest of your conference.